Okay, so I will start with an example. This example of, I think you can see my Jamboard now.
There is some background noise.
I'm writing with a mouse, so the handwriting won't be too good, but okay. So Z mod nz refers to the set of numbers 0, 1 up to n minus 1, and uh, this set of numbers under addition modulo n forms a group. That is to say that there is an identity element which is 0. Every element has an inverse, has an additive inverse. So one's additive inverse is n minus 1, 2 is n minus 2, and so on. And the addition operation is nice enough in the sense that it is associative and closed. Now, let me just give you a brief idea about the definition of group. So, a group is a set, and the set paired with a binary operation such that when AB is in G, A star B is in G, star is associative. There is an element called the identity which satisfies this A star E equals E star A equals A, and for every element in A, there is an inverse of A in G called A inverse, such that A star A inverse equal to A inverse star A equal to, and all that boring stuff. So now, can someone tell me if, is the definition of a group clear, or should I go over it?
It's clear.
Please tell me if I'm. So under multiplication, we know that it is a group under addition. Is it a group under multiplication?
If n is a prime, because
Yeah, because
inverse.
inverse is not exist. Yeah. So even in that case, even in that case, we
But what
consider.
is the inverse of 0?
Okay, I forgot. So you need to remove z. Yes, correct. That's right. So if n is a prime, then you if you remove zero, you get a group under multiplication. If n is not a prime, even if you remove zero, there will be numbers which won't have an inverse, right? So for example, z mod 4z, z mod 4z not. Okay, so in that case, you still consider the group called z and z cross, which is the set of numbers which are co-prime to n. So you pick those numbers from this set which are co-prime to n, and you can see that this is a group.
Sir, one
So
question.
is it clear that?
This so one question. This group which you written z slash nz, is this the group of only the element 0 to p-1, or it is the equivalence classes uh, of 0 1 to p-1?
So for now, think of it as the element 0, 1 up to n
Okay.
minus 1. Only those elements which are co-prime to n, and under modulo, like mul- under multiplication modulo n, right?
Okay.
We
Okay.
will get into the equivalence class thing in a bit.
Okay.
It can be viewed as an equivalence classes of some relation.
Yeah,
Yes.
I have seen
So
like that only. That's why I asked the question to clear that.
yeah, cool. So another example is something called the dihedral group, which is the set of reflections and rotational symmetries. So uh, let R be the clockwise rotation, and let S be the reflection about some fixed line of symmetry. Can someone tell me why there are only two n such elements? Only two n such symmetries, reflections and rotations included.
Still, I didn't get this.
So D2n is the set of reflections and rotational symmetries of a regular n-gon. Is that clear?
Yeah.
Did you-
No, can you tell
So
again
can you
reflections and rotational symmetries?
so suppose that suppose you have a square, right, with numbers vertices, and now you can either rotate it or reflect it about some axis, whichever you pick. Does that the final thing is also something of this form, and perhaps the numbers will change.
Okay.
So if you rotate it, say, you get something like this, and if say we fix this line of reflection, and on reflecting we get. So I think that should be clear. Can someone tell me why there are only two n such symmetries?
I think we can fix the first vertex
We have to
with
we have
n
in all
ways and
in all n minus 1 plus 1 rotations, and then n minus 1 symmetries. So total total symmetries that are possible is n minus 1 plus 1 and plus n minus 1, so 2n.
I think the reason is because s square is equal to 1 and r ki power n is equal to 1. So that's why. Because you can basically for the power of r you can take modulo n, and for the power of s you can take modulo 2. So basically it will become like there are n options for the power of r and two options for the power of s, so 2n numbers.
we can
So
fix a vertex in n ways, and we can choose the next vertex in two ways because we can flip it, so it should be 2 into n 2n.
okay, a lot of these justifications are clear. The one which is not a bit clear is that the justification that since R has order n and S has order 2, this group which is generated by R and S will have order 2n. That won't be true in a general case. We will see in a bit where like the multiplication of the orders or even the LCM of the orders won't be the uh, size of the group. Anyway, so is the definition of D20, I think the definition of D20 is clear. Can
Yeah, yeah,
someone tell me
clear.
why RS is equal to SR inverse? So RS is the so you think of R and S as functions, and you as you
So
apply functions from
first we apply s
right,
and then r. First we apply reflection and then r. I am right or not?
go on.
I mean, for this RS notation, in which in this RS notation, we first apply S or R. I think S.
Oh, we first apply S. We so think
Okay.
of it
Yeah.
as functions, and you
Yeah.
go from
Function
right to left, right?
reflection. Yes. So let me think.
So can you tell the reason why the like the number of elements is 2n?
Oh, so one of the ways to see that is so one can go to, let's say in this case, the square case, one can potentially go to these four places, right? And wherever one goes to, two has to be on one of its sides. I mean, two has to be adjacent to one, right?
Why?
So one can go to n places. Oh, con- uh, because we are conserving the geometry of the square.
Okay.
I mean, so the thing is, how do I explain this? So just believe me for now that if you don't tear the square, or if you just rotate it or reflect it, 1 and 2 will always be, so adjacent points will always remain adjacent.
Okay.
For now, just believe. So let's say that's true, and then one can go to n places, and then you have two options for where two can go, right?
Okay.
So that gives us at most 2n possibilities. So we know that the number of possibilities is at most 2n, and then the thing is that we can actually show all the 2n possibilities, like explicitly construct all the 2n possibilities.
Got it. So when you write r ki power 2, so what does that exactly mean? Like here, right and left doesn't make right and left doesn't make sense.
We apply the transformation
So
two times.
r is the clockwise rotation. Yeah, so r is the clockwise rotation by 2 pi by n, and r square is r of r. If you can think of r as a function, so f of f, r of r is r square.
Okay, got it.
Okay, so the thing is, these ideas are sometimes these ideas are very new, and at least I had a lot of issues when I was first reading it. So I really want you to ask any doubts you want. Even if you want me to explain something from the start, I will do it again. Just feel free to ask anything, because these ideas are very new to you people, I am assuming.
So as you told once that the logic that 2 and logic does not work, that LCM of that ordered thing, that 2 and n ordered thing. So like what is the like counter example for that? When does it work
Ah,
and what is this LCM thing?
so you have the handout, right?
Yeah.
So in the handout, there is a section called generators and relations, something like that, and that has a few problems of this form. I think there are three problems, and one of them is a counter example. I will get to that once I like properly define everything. You can check out the problem if you have handout.
Okay.
Here, the in this dihedral group of R2n, the identity is when we do nothing, right?
Yeah.
Okay.
Sir, I think this fact that RS is equal to SR inverse can be proved by just geometry. Like,
I have found a way.
Yeah,
So what
that's
we do,
true.
what
So
we do is we take this orientation first, one, then in the right side two, and then three and four, and then we then what we do is we reflect across the diagonal two four. Yeah, in that figure, across the diagonal two four. So we get three two one four, and then we rotate to get one two three four. So we first apply RS to get 1 2 1 2 3 4. Now the inverse of R is to do nothing, so we don't do nothing, and then we
the inverse
apply
of R
then
is
we
not to do nothing.
okay. Yeah,
The inverse of
yeah,
R
yeah.
is,
I have to find an other transformation so that I get one, right? That would be the inverse, I think.
yeah.
Okay, okay, so I have to find this.
So R is clockwise rotation by some angle 2 pi by n. What will be the inverse of that?
I
Anyone?
think r to the n minus 1.
Anti-clockwise.
Yeah, R to the n minus 1 or anti-clockwise.
Yeah, R to the power n minus one would be good, but that I think that is hard to visualize. How do we get n minus one times?
So you like rotate it anti-clockwise instead of
Rotating r minus one times.
instead
Okay,
of
so
rotating instead of rotating clockwise n minus 1 time, you rotate it anti-clockwise 1. That should be easier to visualize. Okay, let me just show you the why R is equal to. Well, R is this location.
Yeah. 1, 2, 3, 4.
And okay, what do I need to show? R is equal to SR equals. Okay, I will show that R inverse is equal to SR. So same thing.
Yeah, yeah, okay, okay.
Uh, okay, S is the reflection about this thing. Right.
But we have to prove the result for any S, like we cannot choose S.
Yeah, we take small cases, then we can
Oh,
generalize
but
it.
I have fixed S to be S is the
So
relation about a fixed line of symmetry, right? And if I can show for one line of symmetry
yeah, then
by
we can do for
rotational symmetry, I
general
can show for
case.
any line.
Can you repeat that? Why does showing for one line of symmetry suffices?
Because you can rotate. So any lines of symmetry, any reflection lines of symmetry, they are related by some rotation, right? And
Oh,
anyway, we have defined S to be this. We we are actually proving this for we only need it for this particular case because we have already fixed a line of symmetry, and then we so S is fixed. S is a fixed operation, right?
okay. But like if it is just instead of diagonal 2 4, if we say it is the side 1 2, then I think things will change.
But 1 2 is a side, right? We want 1 2. It's not symmetric. The square is not symmetric about 1 2, right?
1, 3, you mean?
If you reflect about 1 2, if you mean 1 3, then yeah, but that will not actually change. I mean, I can show that case after this is done. So let me do this and then I will show that. So okay, we have 1 2 3 4. We rotate by we rotate clockwise by 2 pi by n. We get this, and then we reflect about this line. We get correct, and then I will have to uh, can you see that? Can you see that?
Yeah. So the
Does this
so first we
line
did
square
R
even?
and then we did an anticlockwise. So those two are inverses, right?
Yeah.
Okay.
So is this diagram clear to everyone?
Sir, I think for here there are 4 sides, but I think for odd number of sides the things will change. For say 5 sides.
Yeah, because then the line will not go through actually two vertices, right? It will go through uh, midpoint of one side. Even in that case, you
We
can
are not
prove.
taking polygons of odd side. We are just taking even sides.
No, we can take odd sides
That's
also.
not
It is
But
no.
I mean by the definition of the dihedral group, let D sub 2n.
That it is a regular n-gon. I have not specified if n is order isn't it?
O 2n is for the order of the group.
So
Okay.
n is the order of the group.
answered that the 2n thing you have constructed. How can we show that all its elements are distinct?
I will leave that as an exercise to you.
Can
So
you give some hint?
clearly,
It's quite easy
yeah.
because
So clearly,
first element is just identity, so we do nothing, and then the second element we can take as just one rotation, and then we can rotate it twice, so we get another reflection which is distinct from R. And we did it thrice, so we get another rotation which is distinct from both R and R2. And then same for reflections.
But
And
it might happen
associated.
that
I
say
think
R is equal to SR square.
I think it might be. Hmm?
Go on.
I think we can prove like this that R is orientation preserving and S is orientation. I mean reversing. I mean, yeah, it changes the orientation.
Oh, but then you have to define what orientation means
Yeah,
properly.
you number one, two,
Yeah,
three, four. If they
it
are
can be
clockwise,
done.
then sorry.
Yeah, that can be done. Yes, I get
Yeah.
it. That is not hard to. Okay, so let me to show that none of these two are equal. So if you have r equal to sr square, right? So one example, let's say, suppose you have something like r equal to sr square. You can actually cancel out the r's and get one equal to sr
But these are functions. How can we cancel?
because there is an
R
inverse. So
inverse. Yeah.
so
Yeah,
I
R
will
in continuous.
you can multiply by r inverse on both sides. I will get into that. So I will get into that in something called the cancellation law in a bit if it's not clear right now.
And so just one last thing, like you show that RS is equal to SR inverse, but like how to prove that in a general case rigorously?
What do you mean by a general case?
Like 4 is a special case, like 4 sides are a special case.
Can we proceed by induction?
I mean, you don't even need induction. So suppose,
Yeah,
let me
yeah.
see if I can draw this. Uh, you just let's say some polygon.
And we have to keep in mind that n can be odd also.
Yeah, that's fine. See, the thing is, okay, let me do it as this. Suppose these are the vertices, right? Uh, thanks, crazy. Just a sec. So let's denote the figure by this order. Correct. And then what does R do? R does this, right? Sorry, not this. Yeah, correct.
Yeah, this is a permutation of the 1 to n. Yeah, right.
Yeah, but not all permutations happen. This is a cyclic permutation.
Yeah, yeah.
I have shifted by one. Is this clear?
Yes,
Yeah,
I got you.
Yes.
So using this, you can prove that R is equal to SR only.
but what will S
It's
do?
not that hard. S. Okay. So we will have to take cases. S. Let's say the line is through one, right? And then if it is even, if n is even, then one and n stay where they are, and I goes to sorry I and n minus uh, 1, 2, 3. Okay, now n by 2 and by 2 I and what's this number n minus I or n plus 2 minus I, something of that form. Yeah, I think n minus I.
So we have to like consider two cases, or is there a way to avoid these two cases?
I mean, it's not that much work. Like, is
I
it?
think we should proceed.
This isn't that hard. This can be done. It's just a bit of case dash.
Okay.
So even if you can't, even if you take cases even and odd, it will still work out in the end. This is not hard. I think once you draw enough pictures, you can easily do it. And I don't really want to spend more time on this. Okay, so is the dihedral is the definition of the dihedral group and the fact that it has two n elements clear?
Clear, clear.
Okay. I will wait for 4 or 5 more people to say clear or type clear in the chat, and then I will move on.
Yeah, it's intuitively clear.
So if you have any doubts, please feel free to ask. People are leaving. Sorry.
Yeah, but I think we can proceed because in we have to revise these things.
Okay, but uh, does anyone have any doubts so far? Please feel free,
No,
because
sir.
I think this is an important part, and
One
this
thing
is an
which was
important
a
part. I
bit
don't.
confusing was that sometimes we included 0 in Z by NZ and sometimes we removed 0.
Oh, so
Where? In the
we
integers
never
module n
removed
or
zero,
is
right?
this group? Oh, in the integers module n.
Yeah,
So
Oh,
let me let me clarify that. Z mod nz always has a zero, right? Z mod nz cross, which is this set, this does not have a zero.
non-zero. Yes, it is non-zero.
okay.
Any more doubts? I mean, it's really hard for me to tell if this is too easy
I think
or
I think
too hard or
if we take in the integers module and cyclic group, if we take n equals a prime and we add zero in the group, then I think it's not no more a group. I think because
the
the
group under multiplication
yeah
or addition. Yeah, so the group
multiplication.
under multiplication is never a group if you add zero.
Yeah,
Zero won't
because
have
if we exclude zero, that is the non-zero group, then then it is a group. But if we include zero, then then one is the identity and zero is extra element. So that does not qualify as a group. Am I right?
yes.
Okay.
So for primes, the only thing you need to do is remove zero.
Yeah.
For if n is not prime, you need to remove some other stuff as well. So let's say for n equal to 4, you need to remove 2. You need to do for n equal to
Yeah,
2, you
because
need to
four is
remove
not
4,
a prime.
0 and so any doubts so far? I mean, even if you can't speak, you can just write in the chat. Uh, okay, I think I have lost a few people, but Okay, let me move on. The set of so another example, the set of permutations of n elements under composition. Again, think of permutations as functions, bijections in fact, and then group- that set under function composition is a group. This is
Which
intuitively clear,
Yeah,
which
right?
it is
composition?
quite clear.
Function composition.
Mhm.
So let me do that. So let's say we have a function sigma which takes 1 to 1 to 2, 2 to 1, and 3 to 6. And you have a function, let's say tau, that takes 1 to 3, 3 to 2, 4 to 2. Can you tell me what sigma of tau? This is the composition. Can someone complete this?
Yeah, first we apply tau. So one gets mapped to 3, and then we apply sigma. So in sigma, 3 gets mapped to 3. So sigma, then tau will be 1 gets mapped to 3 altogether. Then in tau, we for 2 gets mapped to 1, and then sigma, 1 gets mapped to 2. So altogether, 2 gets mapped to 2. And then 3, for 3, we have 3 gets mapped to 2 in tau, and then 2 gets mapped to 1. So altogether, 3 gets mapped to 1.
Correct. So you just need to find the sigma of tau 3
Sir, got it.
and sigma of tau 3. Okay.
I
Any
thought we were
any
mapping
doubts in this?
permutations. No, no doubt.
If this is clear, can you write a yes in the chat? I think I am losing a lot of people, but at the same time, there are chances that this is trivial to a lot of you. So it's hard for me to say. Yeah, okay, sure. So anything particular you have a doubt in?
Uh, we
So
have tau, and tau is a function which take 1 to 3, 2 to 1, and 3 to 2. So so if we talk about the inverse of tau, then inverse of tau would be the function which take all these things to 1 to 3, right?
so inverse of tau will take 1 to 2. Inverse of tau will take 2 to 3. Inverse of tau will take 3 to 1.
Okay, okay. Oh, right, right.
You just reverse the maps. Uh, was that Akshat or someone else?
I think we can
Okay,
proceed.
so you have it. Any more doubts? Yeah, let me just. So, in case this is, some of you will have seen this, some of you will have read napkin and stuff. So, in case you feel bored at any time or things are going too slow, I think the handout has a lot of problems, and I'm pretty sure it will be some of them at least are pretty non-trivial. So you can try them if you are feeling bored at any point of time. Okay, anyway, so let me move on. Another example, the last example I want to give is that this set of real invertible matrices of order n plus n under matrix multiplication. So every matrix has an inverse by definition, and the product of invertible matrices is invertible, and associativity is clear, and
Yeah, substitute is clear.
product of
And
So
for the identity matrix, we just take 1010, right?
this is a n cross n matrix. You need for the identity matrix you take one along the diagonals and zero everywhere else.
Yeah, yeah. I mean that only.
So okay, I think this is clear. So note
These are
that the first
examples
two
of which
examples,
thing?
these are examples of a group.
Groups.
And why is this a
All of
group
these are groups.
G of L of N of R?
Because it has an inverse and an identity element.
So you need to
The student asking may not know what a matrix is.
you need to so if you don't know what a matrix is, you can about it. It's not that important. So do you know what a matrix is? Matrix is.
Yeah, I know it. I forgot some things, but I know like overall.
So do you know what a invertible matrix is?
As much as I remember, I think every non-zero matrix was invertible. Like which
That's not. So consider the 2 cross 2 matrix, 0 1 0 1.
okay.
Determinant
This is not
non-zero.
invertible. Okay. If you don't know what a matrix is, or you are not sure of the matrix, you can forget about this example. It's not that important right now. And I think these examples are clear. The last thing I wanted to point out was that the first two groups were abelian. That is to say that the operation was commutative, and none of these three, the three later examples are commutative. So, any doubts so far? Okay. So let me just.
Why is the second example binary? This 1.3.
So by binary you mean why is this a binary operation?
Like binary operations means composition of two elements, but here we are composing one element with something with a function.
Yeah, but both the elements
And
are
here,
functions.
here the binary operation is function composition itself. So we are that's why we are doing that.
We are composing two functions, right?
Okay, got it.
Both the permutations are functions, and we are composing them. So okay. Anyway, I think people have don't have no doubt. Let me move on. So we have already done this, but let me just do this again. So G comma star is a group if it is closed under the operation. If the operation is associative, there is identity and there are inverses. And this group is called abelian if the operation is commutative, right? So okay, someone solved the first part of the lemma. Someone give me a proof of the first part of the lemma that there cannot be two different identities. Hello, am I audible?
Yeah. I think the reason is simple, but that property for because of property 4, because like it should be direct by property 4. Otherwise, you'd get that if E and F are two distinct identity elements, then E is equal to F, which is like contradiction.
I
And what's
This
your
think
A?
I think the it must be like, suppose E and F are different identity elements, then EF is E and EF is uh, yeah, EF is
EF is both E and F,
yeah.
right?
No, but
what
why
that
can't
proof,
we argue by 4? We can just take any arbitrary element A in G and then A inverse must equal both E and F. So
because
that's clear.
there is an there exists sign, not for all sign.
so
Oh, okay,
every
got
element
it.
has an inverse, but the thing is, okay, that's so the thing is that you may not have any other element other than E or F. In which case, you will have to take A equal to E or A equal to F, right? And in that case, it is same as what uh, Vedant said. You can get E into F is equal to E and F. Correct.
So
So,
how do we get E into F is equal to E and F?
so since E is the identity, E into F is F,
Yeah.
right?
Oh, got it.
And since F
Got
is the
it.
identity, E into F is E.
Okay.
So these are just like minor details. These are not too tricky or whatever. Okay, the second one.
We can prove second one by the existence of the inverse. We can just cancel A. So if B is equal to C, then we multiply both sides. If we take for example multiplication, then we can just cancel it because there is an inverse of A.
But you are using something other than the existence of the inverse, right? Something else also you are using.
I
Yeah,
think we are using that 0 into A is equal to A. Oh, sorry, 0. 0 into anything is equal to 0.
But you are also using the second thing associative. So let me
Yeah.
be pedantic and say, so you have AB equal to AC. You say that A inverse of AB is equal to A inverse of
But
and
in these
then
groups,
you are
are we
changing.
allowed to multiply?
This is the operation, not
This is in the general case.
This
Here
operation.
multiplication is different. Here is binary operation, not multiplication.
Okay, let me just include a star here. So A star B equal to A star C. You multiply by A inverse on both sides. Multiply in the sense that binary operation multiply. A
Yeah,
star
and then by
A star
associative we have
is
A
equal to
star.
A star of
A
B star.
inverse into A is just the identity, so B is equal to
And
C.
then since this is associative, you can change brackets. The star is pretty bad. I know these are boring details, but I just want to make sure that these are clear. Right. And then you get this is identity, this is identity. So identity times B is B, and identity times C is C. Any doubts in this?
No, not at all.
Uh, uh, Other people, you can type in the chat if you. Okay, so similarly, you can show this that you can. We showed that you can cancel on left, and then similarly, you can show that you can cancel on the right. Inverses are unique. Can someone give a proof of this? The fourth point.
Yeah, this is quite easy because previously we proved that identities are in. So if we assume that there are two different inverses, A and B, then then we would get two different identities. So that would not be good. I mean, that would contradict the uniqueness of the identity.
Yeah, correct. So if you have, let's say, suppose both B and C's are both B and C are inverses of A. That is, if you have something like this, you can cancel out the A's as we said, and then you get B equal to C. So the inverse is unique. And this is also uh, give me a proof of 5. The inverse of A star B is same as B inverse star A.
I think multiplying A star B will do the trick.
Yeah, and
Yeah,
associativity.
exactly. So B inverse star A inverse star right. And then since this is associative, the brackets don't matter. A inverse into A is E, B inverse into E is B inverse, and B
But
inverse
sir,
into B is
it
C.
is
So
only
you get the
associative. It is, oh sorry, it is only associative, not commutative. So I think brackets do matter.
brackets won't matter in the sense that if I have, let's say, any such thing A1 star, A2 star, AN, no matter which bracket, I can choose many ways to bracket it. I can do this and something inside. There are many ways to bracket
Bracket
this,
means we can just
but
put
all
I mean, associative means we can just put brackets what wherever we want. It does not mean
We cannot
But sir,
change the order of the elements.
but suppose you have that A. Suppose you want to simplify A into B into A inverse, where A and B are random elements. Then how can associative like relate A and A inverse, where AB is
but
in a
then
bracket?
you are not changing the brackets, right? You are talking about changing the order of the product. I can put bracket on this anyway, right? I cannot write A star B equal to B star A and then argue
yeah,
that
yeah.
this is equal to B.
You're not changing the order of the
But the bracket
appearances.
matter, right? You cannot change the order, but you can.
Oh, okay, okay.
Okay, so uh, enough of being said. And now we define something called the group homomorphism. So given groups G H comma cross, a group homomorphism is a function from G to H that satisfies this property that phi of G1 star G2 is equal to phi of G1 cross phi of G2. Note that the operations are different. This
Yeah, yeah.
operation is the operation from G and this one is the operation from H.
Sir, what is this
Any doubt?
multiplication operation?
Binary operation of H.
Any
So
other
this is not
binary.
your normal multiplication. This is not your normal multiplication. It is some binary operation associated to this group A.
Which is defined on the set H.
Uh, so is this H like can G and H be anything, or they must have some relation?
G and H
No, they
have to
must
be
be
groups.
groups.
That's all.
Can you give one example, please?
So
I think we can wait
so
for
consider
the
the
sir to complete.
consider the map I from G to H, which sends every element of G to the identity of H.
Okay.
Can you discuss
Yeah, yeah, we get it.
that this property is satisfied?
Yeah, got it.
So a group homomorphism is just a function which satisfies this additional property. Right. That's all you need to know.
And if
And now an
the
iso so
only function exists,
homomorphism.
then groups are homomorphic, right?
Yeah, but homomorphic is generally a very weak statement
Okay,
because
okay.
any two groups are homomorphic, right?
Yeah, yeah.
You
We
send
just have
everything
to,
to the identity.
isomorphism is more important because in that case we have to establish the bijectiveness also.
Yeah. So a group homomorphism that is bijective, that is, it covers everything in N. There are no repetitions. Group homomorphism that is bijective is called an isomorphism.
So, sir, can
This
GNH be
isomorphism will cover.
infinite?
Yeah.
Yeah, it can happen.
And is this homomorphism function unique?
No, because I mean it
I think
some it
homomorphism
depends on
function
the group.
can be or cannot be unique, but isomorphism must be unique. I think. Am I right?
Even that's not so.
So
Okay,
there
let me
might be
give
two
you an example.
isomorphic
Right.
functions.
So let's say z mod 4z to z mod 4z. One isomorphism is the thing which sends just a second. This is an isomorphism, and once I have defined for one, the phi of two is phi of one plus one, so phi of one plus phi of one. This is the identity isomorphism, correct?
Yeah. Okay. Okay. So this maps all the elements to itself.
This maps 0 to 0, 1 to 1, 2 to 2, and 3 to 3.
Yeah. Okay.
Correct.
Okay.
Now, can you give me another isomorphism that is
So, can
isomorphism
be
from Z to
phi
mod
of
4Z?
1, 2, 3, and
Yeah,
others get determined uniquely.
yeah, exactly. So 1 to 3, 2 goes to 3 plus 2 equals to 1. 2 goes to 3
Does
plus 3
this
plus 2
Z
equals to
by
1,
4Z
and 0 goes
contain
to 0.
0?
Yeah, it contains zero.
Yes. So if you have a cross here, then it does not contain 0. Otherwise, this contains 0.
Got it.
This is under addition, right? This is under addition, so there are no problems if it has 0. So you have two different isomorphisms from Z0 4Z to Z0 4Z. Okay, in general, how many isomorphisms are there from Z mod NZ to Z mod NZ?
Intuitively, it
Okay, before
seems
that,
that there should be n minus 1.
We can like this, like here for 4
yes,
we have
right
we
here.
can in one isomorphism one can map to 0, and then 1 2 1 so 3. So for n there must be 3. There must be n.
One mapping to zero is not an isomorphism, right? Because everything maps to zero. Then.
Okay, okay. So we have to subtract 1. So n minus 1, I think.
Okay, so before getting into that problem, let me make sure. So, any doubts so far? This so far has been the boring part of the class because I have just been introducing definitions and stuff. Any doubt? Anything you want me to continue? Anything you want me to repeat? Okay, if
No,
not,
sir.
so if you have any doubt, feel free to ask me. And meanwhile, the people who don't have a doubt, think of this problem. Z mod and Z
Homomorphism
mod.
is just a function, so it
So
can be any how ugly is the function, that does not matter. But in isomorphic we must have bijective. That's all, right?
homomorphism cannot be any function. It has to satisfy
Yeah,
this
yeah, yeah.
phi of
With that,
g
with
g1
that
star
version
g2.
also. Yeah.
Yeah,
Okay.
isomorphisms are nicer functions than homomorphisms. Yes.
Yeah, isomorphism sign. We can define primitive roots in that case. I've seen that.
So n minus one is a wrong answer for that problem. Z mod nz to Z mod nz. So try for Z mod 6z. So
But
let's try to
what
think
is
of
the problem?
isomorphisms from the number of isomorphisms from Z mod NZ to Z mod NZ.
And which
Okay.
operation, like
It's
multiplication, addition?
also whenever I say Z mod NZ and I don't say the cross thing, this is under addition.
Okay.
Okay, so this is one. Any other? Yeah, I mean, don't spoil. So can everyone see why the answer is pi up and the Euler tangent pi?
We will try to prove it.
Yeah, so
Yeah, I think we can prove it by primitive root maybe, or something like that.
primitive you don't primitive roots are something needed for multiplication, right? We are dealing with addition here. Primitive roots are things which are related to multiplication modulo numbers.
Yeah, I think the reason is that element one can be get mapped to any number which is co-prime to n. So that's the reason.
Yes, exactly. So anyone has any doubts on this?
I think this is similar to the Cauchy's functional
So
equation.
yeah, in some sense, because it is additive, right? The operation is addition. So the since it is a homomorphism, it has to satisfy phi of x plus y equal to phi
And
of
it
x plus
also
phi
have
of
to
y.
forget about it. Yeah, then 5.
So if you don't have a doubt, type no in the chat. So I have an idea of how many people got this. And if you have a doubt, please, I really want you to ask me.
No doubts, no doubts.
Sir, actually, sometimes I get doubts like these definition of fields, these all things rings differ by a very little thing. So, like, do you know a source from where I can like learn these things?
You can take any abstract algebra book and that will have. So if you see the reference section of the handout, that has a few abstract algebra book. I think three of them, and any of them is good for an introduction.
Okay.
Yeah, napkin is good, but napkin does not really go too deep into it. I mean, it's not possible to cover a lot of stuff in that little space that Ivan uses.
Uh, but like,
Napkin is
how to
great if
remember
you
all these
want to satisfy
properties?
your curiosity.
These properties are quite easy to remember.
Like the fields, like these
Oh,
fields rings differ by a very little thing, only by one two properties.
These does not refer by a little thing. Ring is a set in which we have two operations, I think. So those are different structures. Fields and then vector spaces are different
okay,
structures.
let's not start a fight here. So, roughly speaking, not even roughly speaking, so groups have one operation, rings have two operations, and let's say addition and multiplication, and not everything might have a multiplicative inverse. In fields, everything has a multiplicative inverse. So, groups groups look like Z mod and Z, and ring. So the integers is a ring because you can multiply and add and subtract, but you cannot divide. Right? The integers is not a field because you cannot divide, and things like rationals, reals, complex numbers are fields. Okay,
Okay.
let's not digress too much. Anyway, I think this phi of n thing is clear. So let's solve a
Yeah,
few,
clear, clear.
maybe I should, or maybe I should do the exercise. So 2.4. Let's try 2.4. I don't think I will be able to cover everything I wanted to, but yeah, that's right. It's more important to give you guys a basic idea. So 2.4. I hope the statement of the question is clear.
So here E is the identity, right? In
Yeah, but
141. Okay.
E is defined differently, right? E is defined slightly differently from the normal group identity.
Oh,
E is defined by this first point, and this is different from how E was defined for a group.
yeah, because I think there is an associative word with the binary operation.
And what does
Yeah,
this
that's
line
not
mean?
the.
Set closed under associative product.
This means that the product is associative, and closed means that closed is this property. If A and B are in G, then A star B is in G.
Okay, so only property 3 is a bit modified.
Both 3 and 4 are modified. Any ideas? So here we are playing around with the group axioms,
Yeah, yeah.
testing what things we can drop and what else.
And this dot is a binary operation.
Yeah,
Yeah, I think we can do
Yeah,
this first.
I think G is a group, I think, because E is slightly like uh, identity and Y of A is like
We have to
inverter.
prove that thing.
Yeah, we have to prove that.
Like assume on the contrary that some like there are two e and there is one e and one f for which property one holds true, then we get a contradiction.
okay.
uh,
You need to verify that it satisfies all these four properties, right? That's the thing you need to verify. So you need to prove that E into A is also A, and you need to show that Y of A into A is E. Correct.
oh yeah.
Those two properties are given, so we have to take these one and two properties for granted because they are given in the question.
Yeah, you take 1 and 2 for granted, and then you have to show that 3 and 4 are satisfied. The 3 and 4 of the group axiom. Okay, so let's start writing something.
Sir, I think one thing we can do is
And
that first we show that the identity element is unique. Like assume on the country that AE is equal to A and BF is equal to B for distinct E and F and for some A comma B in G. Then if we multiply the two equations, uh, we would get that AE into BF is equal to AB and then we multiply both sides by A inverse and then by P inverse.
But you cannot multiply by A inverse, right? You are multiplying by
Um,
A inverse on the left. Inverse, you don't know if inverse satisfies the left multiplication thing. You know that inverse satisfies the right multiplication. Like A into A inverse is E, you know, but you don't know if A inverse into A is E.
oh yeah, that's a
Did you?
problem.
So, where do I check? So we have A into E is equal to A, and A into YA, and such an YA exists for any A, correct? And now we have to show that E into A is equal to A, and Y of A into A. Forgive the handwriting. We have to show these two things.
But we have to also show the uniqueness.
No, but because uniqueness can be derived once you show that this is a group. Once you
Okay,
show
yeah.
that these four properties are satisfied, you can derive all these right cancellation, left cancellation, uniqueness, and everything from that.
How can we go about proving the first part, that is closure property? I am not getting how to prove that. Should we assume a
Oh,
group?
closure is given in the question, right? Closed under an associative product. Closure and
Associative product is some
associativity are
different
given.
thing. Associative product is some different thing. What
Associative
is meant
product
by
is a
associative?
binary operation that is associative.
Oh, okay, okay. So associative property is also satisfied.
Yeah.
Oh, okay.
Oh yeah, I think we can do that in the second property, multiply both sides by A.
Multiply both sides of this equation.
The second equation in the question.
A into I of A equal to E.
Yeah, and we know that A is equal to A.
Okay.
Oh yeah,
So
oh sorry,
And
that doesn't give anything.
I think then we get a dot y of a is equal to e dot a. But since this binary operation is associative, so
you
we
get is
can
equal to A dot E.
yeah. So
A
we
dot E,
get
not E dot E.
a dot a.
A dot A.
Please show the second property once again.
If we
You have the
multiply,
handout, right?
Yeah, okay, okay. So what we do is we multiply by a, so we get a dot y of a equals e dot a. So oh no, but we have a dot e.
You get A dot Y of A equal to A dot E.
But okay, but okay, we
Not
get
E dot A, you get A
a
dot E.
dot y of a dot y of a is equal to e, so we get e dot a equals e dot a. So no, what we get? A dot y of a is e. So yeah, so I think we get
Okay,
e
help
dot
us
a is equal
people.
to a dot e.
Uh, it's not right, but uh, okay,
Sir, I think like it should be opposite because
yeah,
like We can only put something after A. How can we ever get something behind A?
I mean, that's the problem.
Oh yeah, I think one thing we can do is that we can show that Y is an involution.
Okay,
So if
then
we replace A by YA in the second property, then we get a YA behind A. So our one thing is done. So we
you
have
get y of a times, you get this right, y of a times y of equal to e.
can you repeat?
You get this right.
But I claim that Y is an
You
involution.
y of a is equal to e. Yeah. What's your proof?
Just a second.
So if it is, if it will be, if you are comfortable with it, you can type on the chat because this
Okay,
y of a y is
let
not
me
there.
think. Just a second. Uh, I think in the second equation, if you multiply both sides by y of a in the right, then y into y of a would change to, uh, it will change to e. Yeah. So and then we know that a is equal to a. So you would get that a is equal to e into y of a. At least this is some progress, I think.
Can you type that in the chat? It's hard to follow the argument.
Okay, I will just write the claim, and I think that is easy to
Okay,
prove.
okay, let me do this. Let me do this. Let me do this. Let me leave this as an exercise. This is not hard. This you just have to do
Yeah,
some
okay, leave it
manipulation.
as because time is running out.
Let me leave this as an exercise. These three problems as an exercise, and all of these are relatively easy.
And what does that
So
sign
let
mean?
me
That congruent sign?
Isomorphic.
isomorphic.
Okay. So we just have to create a bijection.
Yeah,
Yeah.
you have to create a bijection which satisfies the phi of x star y equal to phi of x star phi of y thing. You have to create a bijection which respects the group operation.
Yeah,
Uh,
which is the group
I
action
didn't
because
get the meaning which respects the group operation, like these are groups only.
that condition this
Respects not in the existence, respect in the sense that this phi of g1 star g2 equal to phi of g1
Okay,
cross
got
star
it
g2.
now.
Okay, so let me more definitions. So the order of an element is the smallest n which such that x to the power n is equal to 1. Note that this 1 is not your multiplicative 1. This 1 is the identity of G, right? This 1 is not your uh, integer 1 or real 1 or anything. This is the identity of G. So
okay, okay,
properly it
yeah,
should be x to
one
the power
sub
n
g.
equal to G anyway. Yeah, 1 sub G. And the order of a group. So the order of an element is x to the power n equal to the minimum n such that x to the power n is the identity. And the order of a group is the number of elements of the group. Right.
Yeah,
So
got it.
small exercise. Suppose order of x is n. What is the order of x power? So x power k is x into x into x k times for a positive k. And for negative k, this is x inverse into x inverse into x
I think
inverse.
it should be n upon GCD of k comma
So
n.
yeah, correct. Is that clear to everyone?
Yeah, I think this is similar to the
Yeah,
primitive thing.
the order is clear and all the things.
And
Primitives are much more complicated. Anyway,
what do you
yeah, go
mean
on.
by O of AB is finite? Yeah, this is one doubt. It might happen that. Okay, got it. I didn't read that. Oh, sorry.
So given that O of AB is finite, show that DA and AB have the same order. So even though we don't actually have commutativity, we have something which that is some have even for a general group.
We have 12 minutes left, I think. More.
Yeah, but I don't really want to like get into too many definite bases and not. So we have to that. Oh, we have to show that order of AB. Same as order of B. That is to say, AB power n is equal to E. That's a long E. If and only
I think it suffices to prove one direction
okay.
because if we
Ideas.
can prove one direction, then the other will follow by symmetry.
Yeah.
Sir, got it. Um, Sir, I think
Okay.
AB ki
Go
power
on.
n means A ki power n into B ki power n.
No,
I
AB power n is this times times A.
Okay, then the proof is wrong. I assumed the other way around.
So can you see that this is
Yeah, yeah, got it.
now? Can you finish? I'll tell you proof.
First multiply on the left by A inverse and then on the right by B
Okay.
inverse. So that gives us that BA ki power n minus 1 is equal to A inverse B inverse, which is equal to AB inverse. And then,
Uh, Not AB inverse. You get A inverse B inverse. This is not
yeah,
AB inverse.
Yeah, yeah. A inverse B inverse. Right.
This is BA inverse.
Why?
Oh, we proved this, right? This thing, fifth property.
Yeah.
Uh, can you repeat the proof once?
So you just
We
multiply
just use
both
the
sides by a
associative
star,
property
and then
by multiplying A.
I think I still have it written in some. Yeah, this.
Yeah, yeah. Written,
So
written.
B inverse star A inverse star A star B. You can remove the brackets. I mean, the brackets don't matter. You get you get that this is E. Is that should I go over the steps?
No, no, got it. Got it.
Okay. So yeah, we had this. Uh, this mouse is very hard to control. We get that dA power n minus 1 is equal to A inverse B inverse, which is just BA inverse.
Yeah, fine.
Now can you
Yeah, now it
now
is
can you
easy. Just multiply both sides by BA.
Yeah, BA, BA.
yeah, exactly. So is that clear to everyone?
What was this property?
Anyone has any doubts in that?
What we are
Which
proving?
one?
Yeah, this right here. What we are proving currently.
This problem.
Yeah, yeah.
You prove that AB and BA have the same order.
Oh, okay. I see. I forget about the problem. Just trying to solve it.
Yeah, that helps. So okay, let
Yeah,
me
okay. So the proof is complete. I think.
finish this section. Yeah, yeah. So let me just finish this section and we will do another session if we want to. So okay. A group is called cyclic if every element of G is of the form x bar 2. So G can be written as 1 comma x square comma x cube and so on. So Z mod nz is cyclic, and then in fact you can show that this group is the same as any finite cyclic group is the same as Z mod nz for some Z. And
How?
so another thing, given two group, yeah. So suppose you have a cyclic group of order n, right? So that means you have a cyclic group of order n finite. Uh, uh, so that means that your group looks like 1 comma x square uh, up to x to the power n minus 1.
I have a
Correct.
counter example. If you consider the group 2, 4, 8, 16 modulo 32.
2, 4, 8, 16 under multiplication.
Yeah, modulo 32.
So you need zero.
Yeah.
2 times
So
16 is 0.
then only it can be a group under addition.
This is same as z mod 5z, correct? You send 0 to 0, 1 to 1. I mean, sorry, not 1. 2
Oh,
to
so you are
1,
talking about
4
isomorphism.
to 2. Yeah, yeah, yeah.
Okay, so you are
So
claiming that
you
any
already
group with order
z mod
n is isomorphic with z by nz.
if the order is finite, yes.
Yeah, yeah. Okay, okay. Order must be finite.
What do you mean by finite order?
No, yeah,
There must be finite number
order
of
by
elements.
definition is finite, but So the order of one in the group of integers, the all the integers, the order of one is infinite, correct? And integers is a cyclic group
Yeah, okay.
because everything can be written as one plus one something, one plus one plus one, or minus one plus minus one plus minus one, some number of things,
Yeah,
Okay.
yeah.
correct?
So
Uh,
basically, cyclic group is a group in which we can just write any element in terms of strings of the identity.
Not the identity. Strings of the identity is the identity only, right?
Okay.
So I think I should address this. So the point I want to address is that sometimes zero is the identity, sometimes one is the identity, and it is very easy to confuse it. So, for example, in the ring of integers, one is not the identity because it is a group under addition.
Yeah,
So one
because
is
and
not the
then
identity,
we have one
and
more
I think
operation.
yeah, but oh yeah, sorry, I mentioned reading. Okay, so x can't be the identity. I mean, if X is the identity and G is cyclic, then G has to be the trivial group consisting of
Oh,
only
yeah,
one
yeah,
element.
yeah. Trivial group in which we have only one element, I think.
Yeah. So, any doubts so far? Okay, I will just introduce direct product and end the class. So, given two groups G comma star and H comma cross, this set product is a group under this operation. You
It's a
do
set of ordered
so
pairs.
for the elements of G, you do
Yeah,
the operation.
Cartesian products.
Yeah, the
Just
set
like
of
Cartesian
ordered.
products. Okay,
The
okay.
yeah, just like Cartesian product. Correct. You do pointwise operation. So for the elements of G, you operate by the operation of G, and for
Yeah, this is quite easy to
so on
understand.
for H. Okay, so I will leave you with these problems. So this problem, the last problem, is essentially a problem about primitive roots. If you know what a primitive root is, and if you don't know, you don't have to. You can forget it. But yeah, this problem is same as so. When is Zn cross cyclic? This is the set of integers which are co-prime to n. This is cyclic exactly when there is a primitive root mod n.
Yeah, yeah. Because
For
we
people
have
who know
the
what it is.
order of all elements p minus one in case of prime p.
Uh, sir, can you repeat?
So if Zn cross, which is the set of elements which are co-prime to n and less than n, that group is cyclic if and only if there is a primitive root modulo n.
Oh yeah, yeah, that is fine. That
And
is
I think
clear, I think.
and I think that
Because
is
the
clear because the primitive are
primitive
defined
root
like
is inherent
the
in the prime
order
set.
must be phi of n.
Yeah, exactly.
Okay.
So okay, let
So, sir,
me
like after the class, when we solve these problems, like when we try them, so like should we discuss them or like what should we do to verify our answer is correct? Because I'm new to this topic a bit. So
Discord.
you can discuss you are on the Discord server, right? Like,
yeah.
if you are not, you can join the Discord server. You can discuss there. You can ask me, and that should be good enough. Okay, so let me end the class here. And
Yeah, okay.
I
Thanks.
really